Welcome to the Narako Deep Dive, the show where we break down the latest research and science around learning, memory, and on some days, anything else that catches our eyes. So let's jump right in. Today's topic. I hope you enjoy.
You touch a hot stove once, and you never do it again. No repetition, no flashcards, no 1,000 tries. And for 70 years, neuroscience had no real explanation for how that's even possible.
Right, that always kind of bugged me, actually.
Turns out, a single neuron can rewrite its own wiring, permanently, in a window of 6 to 8 seconds after the moment it happens.
Wait, seconds? That just broke a rule I didn't know was a rule. This is the Narako Deep Dive. I'm Ray, with Ellen.
Hi.
Today, how your brain rewires itself in seconds, and why the smartest machines on Earth still can't. Okay, so normally when we talk about a diagnosis, there's this expectation of proof, right? You break your arm, they slap the x-ray up on the light box, and there's this stark, white, jagged line just sitting there. The doctor points at it and goes, "Yep, that's broken." And honestly, you feel weirdly relieved. Your pain finally has a picture. But the second you try to do that with memory, with learning, there's no light box. There's no jagged line. Something in your head genuinely changed today, and no scanner on the planet can show you where.
And that's such a human thing, wanting that kind of picture. We crave visible, categorized certainty, something you can point at and say, there, that's the damage, that's the fix. But the whole landscape of neurodevelopment, memory, learning, it's not blurry, it's invisible. The machinery is absolutely working in there. We just can't watch it happen.
Which is a strange place to start a science show, honestly. Here's something huge, and also, nobody can show you a photo of it.
It really is, which is exactly why it had to be pieced together sideways instead, inferred from 3 fields that don't normally sit at the same table.
Right. Which ones?
Cellular biology, functional neurology, and computer science. On paper, totally unrelated, but every one of them keeps circling back to the same question. How does a network, a brain, or a machine actually take something in and hold on to it? So here's the thing about Cajal, and I don't just mean he was cautious about the adult brain, he was absolute about it. Santiago Ramon y Cajal, the man they call the founder of modern neuroscience, the one who first showed neurons as separate individual cells instead of one continuous web. In 1928, he wrote that in adult centers, the nerve paths are fixed, ended, immutable. Not mostly stable, not slow to change. And for most of the 20th century, that sentence wasn't a hypothesis anybody was still testing. It was the central dogma. You learned it like a law of physics.
Immutable. Okay, that's a bold word to build a whole field on.
It really was the whole architecture. The adult brain as a finished product, wired once in childhood, then locked for good. Which meant if you had brain damage as a grown adult, the assumption was, well, that circuit's gone. Find a workaround. It's not coming back. That held for decades, until researchers actually went looking and found neural stem cells, cells still capable of becoming brand new neurons, quietly working inside adult brains. There's research tracing exactly this shift, how discovering those stem cells and ongoing adult neurogenesis didn't just tweak Cajal's old claim, it shattered it, and forced a complete rethink of how the brain heals and recovers from disease.
So the whole finished product idea was just wrong this whole time.
Wrong, and wrong in a very specific way. Because what replaced it isn't one tidy new rule. It's this whole toolbox. Neuroplasticity, that word we throw around constantly now, covers everything from a single synapse getting a little stronger, all the way up to entire networks physically reorganizing after an injury. Small tweaks, big rewiring. Same underlying capacity, just running at different scales.
Circuit board to toolbox. That is quite the demotion for a 100-year-old theory.
So here's the thing. For 70 years, there was one golden rule that explained all of this. 1949, a Canadian psychologist named Donald Hebb writes it down, and it becomes basically scripture in neuroscience. You've probably heard the shorthand. Neurons that fire together, wire together.
Yeah, I've said that phrase 100 times and never once knew who actually said it first.
Well, hold that thought because it's a little more complicated than Hebb said it. But first, the mechanism. The actual rule requires two neurons to fire within milliseconds of each other, and that has to happen over and over and over. There's research on exactly this timing requirement. The window is narrow, the repetition has to be relentless, or the connection doesn't budge.
Okay, so give me the concrete version. What does that actually look like?
Picture learning a piano chord.
Oh, I like where this is going.
You play it once, nothing. Twice, barely a ripple. But you play that same chord 1,000 times, and those exact neurons fire together 1,000 times, and the physical connection between them gets thicker, faster, stronger.
Until the pathway is basically a superhighway.
Exactly, a superhighway. It's essentially rote memorization happening at the cellular level. Flashcards, scales, times tables. Hebb's rule handles all of that beautifully.
Okay, that part actually makes total sense. So back to my question. Hebb gets credit for this, but you just said, hold that thought?
Right, because the truth is, theorists were circling this exact idea decades before Hebb published anything. He didn't invent fire together, wire together out of nowhere. He crystallized a bunch of earlier, messier ideas into one clean, quotable rule, which honestly is its own kind of genius, packaging 70 years of theorizing into 8 words.
Okay, hold on though. I have to push back on this one, because something about it isn't sitting right with me. If Hebb's rule needs a synapse to fire together with a partner hundreds, maybe thousands of times, and it has to happen within literal milliseconds of each other, every single time, then how do you explain the stove? You touch a hot stove once, and you never do it again. Not after 10 tries, not after 100. Your brain just gets it. So either I'm missing a step here, or that 70-year-old rule has a hole in it the size of a dinner plate.
No, you're not missing a step. That's the actual hole.
Wait, so it's a real problem? Not just me being slow on the uptake?
Not even a little. Hebb's rule is fantastic for the slow stuff. Flashcards, scales, vocabulary, anything built on repetition. But hand it a single, terrifying, once-in-a-lifetime experience, and the math just doesn't close. There's actually a paper that lays out the classical model plainly, and it's pretty blunt. Effective Hebbian plasticity depends on tightly timed coactivation, repeated over and over, to produce any lasting change. Nothing in that framework has a slot for learned it permanently in one shot.
So by the textbook rule, I should theoretically still be touching that stove.
By the textbook rule? Kind of, yeah. And this isn't just you and me noticing it. This gap has bugged neuroscientists for decades. Everyone sort of shrugged and figured there had to be something else going on underneath.
Great. 70 years of, there's probably something else going on. Very reassuring, guys.
So here's the thing. Around 2015, 2017, a researcher named Jeffrey McGee and his team were recording from mouse hippocampus. That's the brain's memory and navigation center. And they caught something on the tape that just didn't fit any existing rule. They called it Behavioral Timescale Synaptic Plasticity, BTSP for short. And the short version is, a single dendritic event can permanently rewrite a connection, no repetition required, unfolding over several seconds instead of milliseconds. That's not a tweak to Hebb's rule. That's a different rule.
Okay, wait. This is the missing piece? The thing that explains the stove?
This is the missing piece. But to get why, we have to zoom into the dendrite. That's the branching little antenna arm of a neuron that receives signals from other cells. For decades, everyone assumed dendrites were passive, just wires carrying a signal down the line, nothing interesting happening locally. And this is the part that gets me. McGee's team found dendrites aren't passive at all. When enough input converges on one at the right moment, specifically from two different brain regions, CA3 and the entorhinal cortex, arriving together, the dendrite doesn't just pass a signal through. It generates its own electrical event.
Its own event. Like it's making a decision.
Sort of, yeah. It's called a plateau potential. Instead of a quick electrical spike that fires and vanishes in a millisecond, the charge shoots up and just stays there, elevated, for hundreds of milliseconds, sometimes a full second or more. And here's where it gets absurd.
Wait, how long again?
I'm getting there. That plateau doesn't just sit there being weird. It reaches backward and forward in time. Any synapse that was active anywhere from 6 to 8 seconds before that plateau, or 6 to 8 seconds after it, gets permanently strengthened.
6 to 8 seconds. In neuron time, that's basically geological.
It's an eternity, genuinely. Neurons normally operate on a millisecond clock. This is a mechanism reaching across a window thousands of times longer than a single spike. And there's a well-known paper published in Science where McGee's group showed exactly this in live mice. A single plateau event was enough to carve out a brand new place field. That's the specific location a neuron fires for, in one trial. No 1,000 repetitions. One dendritic event, one memory, locked in.
So the stove isn't the exception to the rule anymore. It is the rule. We just didn't have the mechanism until now. Okay, wait. So in between the actual touch and that plateau locking things in, something has to be holding the information, right? Like a waiting room. What's it actually doing in there?
Not quite a waiting room, more like a temporary mark. The instant that experience happens, the specific synapses involved get flagged as active. That flag alone doesn't lock anything in. It's the plateau signal, if it shows up while the flag is still live, that decides which marked synapses actually get made permanent.
Oh, okay. I've got the image now. You know when you're reading something dense and you've got a highlighter in your hand? You're not stopping to memorize every sentence as you go, you just mark it. That one's important. That one too. You don't even know yet if it's going to matter later. You're just flagging it. So that flagging pass is the highlighter. It marks which synapses were active around the moment, but nothing's actually saved. It's temporary. If nothing else happens, the ink just fades. But if that plateau shows up inside the window, that's the moment somebody actually goes back through the highlighted parts and copies them into permanent notes.
Yes, exactly that. And here's the part that gets me. The plateau isn't just present when that happens. It's doing the choosing. There's research looking at exactly this in the hippocampus, and it shows these plateau events act like a gate, deciding in real time which of those highlighted synapses actually get the ink made permanent.
So the highlighter alone commits to nothing.
Nothing. Left alone, that highlighted mark just quietly fades. But there's a review pulling together this whole line of work, and it makes a pretty striking claim. A single plateau event, just one, is enough to lock a whole set of tagged synapses in permanently. No repetition needed. That's not just a metaphorical lock either. It's a real, lasting structural change at the synapse itself.
So the save button isn't a metaphor. It's an actual construction crew showing up on site.
Basically, yes. Okay, but that construction crew still needs to know where to build. And that's the harder problem. At any given moment, you've got something like 80 billion neurons in there, and huge swaths of them are firing constantly. background noise, totally unrelated stuff. So when you touch that stove, out of that entire storm, the system has to isolate the exact handful of synapses that actually caused the pain. Not the ones next door, not the noise. This is what researchers actually call the credit assignment problem. Who gets the credit or the blame for what just happened?
Right, because if the brain just panicked and flooded the whole system,
You'd learn completely the wrong lesson.
like the song that happened to be playing on the radio when you got burned. Now you're weirdly terrified of that song instead of the stove.
That is exactly the failure mode, and it's a real risk. A global reward signal smears credit across everything that happened to be active at the time. BTSP avoids that entirely. There's a review that lays this out really clearly. It calls BTSP a non-standard credit assignment mechanism because it solves the problem without freezing the rest of the network. It just looks backward and forward across that 6 to 8 second window and only touches the synapses that were actually tagged. Surgical, not a blast radius.
So it's not scanning 80 billion neurons trying to guess. It already knows because of the tag.
Exactly. The eligibility trace already did that filtering for it. And this isn't some rare trick happening in a handful of oddball cells either. There's work looking directly at that hippocampal region, CA1, and it found a substantial fraction of those neurons showing this exact one-shot signature during learning. This is happening at the population level.
Huh. So it's not a fluke. It's just how the whole place runs.
Right. That's the default, not the exception.
Okay, wait. This is also the part where I get a little nervous for myself, honestly.
Nervous how?
Because if my brain can permanently save a lesson in one shot, I have made some real weird lesson candidates over the years.
Go on.
In college, I stepped on a Lego barefoot at 2 a.m., screamed loud enough to wake my roommate down the hall. And now, 20 years later, I still flinch walking near carpet in the dark. Doesn't matter that there hasn't been a Lego in that building since 2004.
Congratulations. Your hippocampus filed that under permanent threat.
That's exactly it, right? One plateau potential and boom, carpet equals danger, locked into the architecture. Forever.
Pretty much. It's efficient. It's just not always picky about what it decides is worth keeping.
That's not reassuring, Ellen.
It wasn't meant to be. Because what happens when this fast, one-shot save button locks in the wrong lesson? That's exactly where we're headed next.
Oh, good. Can't wait. Okay, wait. Zoom out with me for a second. A single strengthened synapse is microscopic. How does that turn into me actually navigating a whole city? Or clocking that my coffee shop moved across the street?
So here's the thing. The hippocampus was never storing these memories as isolated dots on a page. It's building something closer to a living map. And it doesn't build that map alone. There's a neighboring region called the entorhinal cortex. Think of it as the hippocampus's scout, constantly feeding it information about what's out there in the world. And what's wild is that this scout doesn't just deliver raw information. It sends what researchers call an instructive signal, meaning it's not just saying, here's what's happening. It's saying, here's what matters. Pay attention to this. And that signal is what decides where and when your hippocampal cells actually turn into what we call place cells, cells that fire when you're standing in one particular spot.
Huh. So the map isn't neutral. Something's grading it.
Exactly. And this is the part that gets me. Watch what happens when one location suddenly matters a lot. Say it starts predicting a reward. Both the entorhinal signal and the density of place cells in the hippocampus pile up right around that cue. The whole map physically reorganizes around whatever's newly worth caring about. There's a study where researchers went in and silenced that entorhinal signal directly, just switched it off, and that entire reorganization around the reward cue basically vanished.
Wait, so it's not the hippocampus deciding on its own what matters. It's being told.
Right, that's the reframe. It's less hippocampus independent genius and more hippocampus extremely responsive student taking direction. The signal from the entorhinal cortex doesn't have to change to shift what matters. It can just get redirected, pointing the hippocampus's attention somewhere new. That's part of what lets your whole map reorganize almost instantly around a new priority.
Okay, so that's why I can walk past my coffee shop's old empty storefront 10 times and still glance at the door out of habit.
Your map got redirected, but some piece of the old signal is still lingering in there, apparently.
Great, my brain. Still filing paperwork on a coffee shop that closed months ago. Okay, but here's what I keep circling back to. What actually happens when the animal just stops? Just sits there, not exploring, not doing anything at all.
So here's the thing that genuinely surprised me the first time I read this research. A stable place cell, one that fires reliably in the exact same spot day after day, isn't actually just sitting there unchanged underneath. There's a study that tracked these cells across repeated visits to the same environment. And what they found is that even the supposedly locked-in ones get rebuilt. They essentially re-earn their spot through that same plateau and tagging process every single time the animal comes back. It's not encode once, done forever. It's more like the memory gets quietly re-verified, re-saved over and over.
Huh. So stability isn't the absence of change. It's just change that keeps landing in the same place.
That's a good way to put it, and it's not some rare edge case either. Across that same hippocampal region, a genuinely large fraction of the neurons show this rapid single-shot signature, not just on day one, but trial after trial, day after day. This is the dominant way these maps get built and maintained, not some backup system running quietly in the background.
Okay, wait. So where does actually resting fit into all this?
Right, and this is the part that gets me. The mechanism itself, the plateau, the tagging, that's fast, seconds, wide awake, happening in the moment. But folding that one fresh update properly into the whole existing map without wrecking anything else around it, the evidence points to that happening especially when the animal goes still. Quiet rest, not necessarily deep sleep. And this lines up with the original discovery of this mechanism back in 2017. It operates in exactly the hippocampal circuits that store and retrieve personal, episodic memory, on a timescale that actually matches how we experience remembering something, not the millisecond window the old Hebbian rule demanded.
So the update happens in the moment, but the actual filing happens later, when you're not doing anything at all.
Exactly. Which is a strange thing to sit with. The doing nothing isn't a pause in learning. It might be the part where the learning actually finishes.
Okay, hold on though. I want to push on this because it's been bugging me. If one bad experience is strong enough to physically fuse a connection, say I take a new route to the coffee shop, some dog comes flying out of a yard, I nearly have a heart attack. Does my brain just torch the whole map of that neighborhood? Now I'm avoiding the entire block, not just that one yard.
That's exactly the right thing to worry about. Because on paper, yeah, something that powerful happening in one shot should be able to do a lot of collateral damage if nothing's holding it back.
Right, that's kind of my whole point.
No, I know, and here's where it actually gets tested. There's a human study where people got a single unpleasant pairing. One image, one jolt of pain, just once. Later, they showed people that same image and watched what the hippocampus did. It wasn't lighting up in some generic danger way. It was reconstructing the specific scene tied to that one moment. And how strongly it did, that predicted exactly how much pain the person remembered feeling. Not a flood, a targeted reconstruction of one particular memory.
Huh.
So it's not smearing fear across the whole map. It's finding the one page and reopening it. And this is really the core design problem any learning system has to solve, biological or otherwise. Researchers frame it as the stability plasticity dilemma. Stay flexible enough to learn something instantly, but stable enough that one bad afternoon doesn't erase everything else you already know.
So the dog gets filed under that 1 yard, not under the neighborhood is now hostile. That's actually a relief.
Mostly, yeah. Though ask me again after we talk about what happens when that filing system breaks.
There's a thing that used to genuinely bug me about how medicine treats brain stuff. Somebody goes in with brain fog or vertigo or chronic pain that just won't quit. They get the MRI, it comes back clean. And clean apparently means you're fine, there's nothing wrong with you.
Which is maddening if you're the one actually living in the fog.
Right? Like, the hardware review passed, so tough luck. But there's an analogy from this field, functional neurology, that finally made it click for me. Picture your brain as a smart home, not fixed wiring, an actual live network. Now say one motion sensor goes bad. Suddenly the lights are strobing at 3 a.m., the heater kicks on in July, the alarm's screaming for no reason. The whole house loses its mind over one faulty sensor. And the old school response is either, well, the walls aren't collapsing, so the house is healthy.
Or just rip the sensor out of the wall so the alarm shuts up.
Exactly. Neither one actually fixes it.
Right, because the fix is neither of those. You recalibrate. You get the sensor talking to the thermostat correctly again. That's essentially the clinical move here. Instead of hunting for structural damage that was never there, you treat the nervous system as software stuck in a bad loop, and you feed it new information to break the loop. Very specific vestibular work, that's inner ear balance training, or oculomotor exercises where you track a target with your eyes in precise, deliberate patterns.
Okay, but that just sounds like homework. Eye yoga.
That's exactly what it looks like from the outside. But here's the part that actually ties back to everything we just spent this whole episode building. Those exercises are precision-timed sensory input, engineered specifically to trigger the same dendritic plateaus that drive BTSP. They're not busy work. They're manually pressing the save button over and over until the network overwrites the broken pattern with a working one.
Wait, hold on. So a physical therapist watching your eyeballs move is deliberately doing, on purpose, what a hot stove does completely by accident?
Pretty much, yes.
Okay, that reframes do your eye exercises from mildly annoying to actually kind of incredible.
It's one of the more satisfying spots where the cell biology and the clinic just shake hands.
Okay, wait. If humans can basically hack this on purpose now, surely the machines we built to copy the brain can pull off the same trick, right? Learn one new thing, move on?
Oh, this is my favorite irony in the whole story, honestly. Right now, you've got AI models that can pass the bar exam, write working software, summarize a library's worth of documents in seconds. Genuinely superhuman stuff. But hand that exact same model one new fact, an address that changed, a rule it needs to learn, without retraining the entire system from scratch. And it doesn't just quietly learn it and move on. It falls apart. And once that knowledge is gone, it's not misplaced somewhere waiting, it's just gone. There's actually a name for this failure, and researchers flagged it as early as 1989. Catastrophic forgetting.
Huh. Wait, 1989?
Right, it's an old problem wearing a very expensive new suit. Here's the mechanism. These networks learn by adjusting a huge set of internal numbers, their weights, to get better at whatever task you're training them on. When you introduce something new, the network doesn't gently make room for it. It wildly overcorrects. Picture moving one new piece of furniture into an apartment, and instead of just shifting a lamp, you gut every other room to fit it. That's roughly what happens to the weights holding the old knowledge. They just get overwritten. There's no dial for just the right amount of change. It either barely learns the new thing at all, or it torches everything else trying to.
So it's not that it forgets a little, it forgets Everything it isn't currently staring at?
Pretty much, yeah. And that's the stability plasticity dilemma we mentioned earlier, taken to its absolute worst extreme. There's a well-known analysis of exactly this trade-off, and it lays it out simply. Too much plasticity, and you get catastrophic forgetting. Too much stability, and the system can't generalize or adapt at all. And there's a broader review of how these networks actually get built that backs this up. Training one sequentially on new tasks reliably overwrites the weights that mattered for the old ones. Every single time. Our brains have that offline replay step, smoothing new memories into the old map without erasing it. These systems just don't have that.
So we built something that can write a legal brief, and it still can't learn your name without forgetting its own?
Pretty much, yeah. And it's not like engineers just shrugged and gave up. There are three main patches people use to fight this. None of them are cheap.
Okay, hit me. Patch 1?
Regularization. The most famous version's called elastic weight consolidation, EWC for short. The network basically does math to figure out which weights mattered most for the old tasks, and then it mathematically punishes itself for moving those too far.
So it's basically superglue. Glue the important connections down so they can't budge.
That's exactly the word people use for it. Virtual superglue.
But superglue doesn't come free, right? What's it cost you?
Speed. Whatever's glued down can't flex, so learning the new task gets slower and clunkier. You're trading plasticity for stability.
Okay. Patch 2?
Rehearsal. You save a huge stash of old training data, and every time you teach the network something new, you also make it restudy the old material at the same time.
Wait, every single time? It has to relearn everything it already knew?
Every time. Which means gargantuan amounts of computing power just to keep old memories from slipping away.
That's not learning. That's just permanent cramming.
Basically, yes. Patch 3 is a bit different. Memory-augmented networks. You bolt on an actual external memory bank, so the system isn't trying to cram everything into its own internal weights.
So it's outsourcing the memory instead of actually absorbing it.
Right, storage gets split off from processing entirely. There's a well-known review of continual learning that lays out exactly these families of fixes: regularization, rehearsal, memory add-ons, and it's honest about it. Every single one is a workaround, not a solution.
None of that sounds anything like a brain just holding a charge for 6 seconds and hitting save.
No, not even close.
Okay, hold on. Has anyone actually just tried it? Taken the real BTSP math and built it straight into an artificial network instead of duct taping around the problem?
They have. There's a generalized mathematical version of it. Researchers call it GBTSP. And someone took that rule and dropped it directly into a small artificial network. No superglue, no rehearsal, none of the workarounds we just walked through. And for simple, shallow networks, it worked. The network could build place field-like maps, the same kind of internal representation a rat builds of a maze, and solve basic one-shot matching tasks. One exposure, done.
Wait, seriously? So the actual biological rule just transplants?
For a shallow network, yes. But then they made the network deeper, more hidden layers, more of the internal processing stages you'd need for anything realistic, and it fell apart.
Of course it did.
Right, there's always a catch. So here's the actual reason, and this is the part that gets me. In a real brain, that plateau potential, the save button signal, happens locally, right at one physical dendrite. It doesn't need to travel anywhere. But in a deep artificial network, you've got dozens of virtual layers stacked between the outcome and the specific node that deserves credit for it. Try to route a delayed, seconds-long signal backward through all of that to update one node, and you get mathematical chaos. The exact credit assignment problem we talked about, just insurmountable at that scale. One review of this literature describes it as a stability-plasticity dilemma that only gets worse with depth, not better.
So the deeper and more capable you make the thing, the less it can do the one trick that made it interesting in the first place.
exactly backwards from what you'd want. Another paper on BTSP itself makes the same point from the biology side. Its whole advantage comes from being local, from living on one physical piece of hardware. Ask it to run on something with no physical dendrites, just layers of numbers, and that advantage doesn't survive the trip.
So it's not solved. It's just a very promising dead end so far. Actually, sitting with that dead end for a second, it's kicking something loose that feels bigger than the engineering problem. Say they do eventually crack it. Say some lab actually gets BTSP running cleanly inside a deep network, credit assignment and all, sorted.
Okay.
Then the AI isn't just borrowing our trick anymore. It's running our trick. And our trick doesn't come with a warranty, does it? You said it yourself a second ago. The whole advantage of BTSP is that it's instant and it's local. One dendrite, one experience, permanently written in.
The same mechanism that lets a person walk away from one terrible night carrying something like trauma.
Exactly. No repetition required, no cooling off period, no committee review. It just locks. So if we hand a machine that exact mechanism, don't we also hand it the failure mode that comes bundled with it? Could an AI get stuck in its own version of a flashback? Some maladaptive loop it can't reason its way out of, simply because the update already happened at the hardware level, the same way ours do?
Huh. I don't have a clean answer for that.
So would we need an artificial version of Antonucci? Something that goes in and manually re-triggers a plateau just to overwrite one bad save?
Genuinely? Maybe. If catastrophic forgetting and one-shot learning turn out to be two sides of the same coin, then the vulnerability probably rides along with it too. You don't get to keep the instant save button and throw away the risk that one bad save corrupts the whole file. That's not a solved question. Honestly, it's barely even an asked one yet.
That's a genuinely unsettling note to end on.
It is. Maybe that's the actual lesson in all of this.
Okay, let's climb back out of the machine trauma rabbit hole for a second. I don't want to leave everyone just staring into that. Let's zoom out. What did we actually learn today?
Please, yes. Let's land the plane.
So for basically 100 years, neuroscience treated the adult brain as finished. Fixed wiring, no updates available. Then we accepted plasticity, but we still assumed change only came from slow, grinding repetition. Thousands of reps, perfect millisecond timing. What BTSP actually shows is that both of those assumptions were wrong in the exact same direction. Your brain can physically rewrite one connection in about 6 seconds from a single experience, as long as that experience actually mattered.
That's the part that sticks with me. It's not that repetition stopped mattering. It's that the brain has a whole separate, much faster channel reserved for anything significant enough to deserve instant treatment.
Right. And that's not just theoretical. We watched actual clinicians manually trigger that same 6-second window with eye exercises and balance work, recalibrating brains an MRI would call perfectly fine. Meanwhile, the most advanced AI on the planet still can't pull off the one-shot version without either forgetting everything it already knew or burning a server farm trying not to.
Which might be the most humbling comparison in the whole episode. Your brain just does it. For free, quietly, constantly.
In the last piece, none of that new wiring actually holds without the replay that happens while you're resting or asleep. So sleep isn't downtime from learning.
It is the learning, or at least the half that makes it permanent.
Which is honestly the whole reason we wanted to do this episode. Once you know your brain actually runs on novelty, real stakes, spacing things out, testing yourself instead of just rereading, and sleep, that stops being trivia. That's a design spec. And that's basically what we built Narako around, engineering the conditions your brain already wants instead of fighting it with more repetition.
It's the difference between knowing how the engine works and actually turning the key.
Exactly. So if any of this changed how you think about your own brain today, come learn with us at narako.com. We built it around exactly this science. See you next time.
Well, that wraps up our episode. If you're still listening, I wanted to thank you for sticking with us through this journey. And we hope you learned something new, as that is our goal with the Narako Project, to teach people new things and help them remember them. We hope to see you next week again, where we will continue to tackle and dive into even more interesting topics. Have a nice rest of your day, and thank you.